Well, we are finally ready for some new material here. So 1.5 is on limits. And in everyday language, people talk about limits like a speed limit, the limit of your endurance. Wrestlers have a weight limit. A spring, if you're stretching it, it has a limit to how much it will stretch. And let's say that we have a spring that it will stretch up to 10 pounds. So like you put on a weight of 10 pounds or higher, it breaks it. But we want to see then how long that string will stretch as it gets closer and closer to 10 pounds. Well, that's what we're going to be looking at here. So kind of keep that example in mind. So here's the notation for a limit. So we have the limit of f of x, so this is going to be a function where we're going to replace this with different kinds of functions. And then we're going to look at x values as they approach some constant. And then that number that it approaches is referred to as the limit. Okay, so the way you would read this then is the limit of f of x, and maybe f of x will be x squared or something, as x approaches c. So this arrow means as x approaches c, this arrow here. So it's like what number are we getting closer to? The limit of the function then is the y value of it. So we are looking to see what's happening to the y value as the x is approaching some number. All right, there are several ways to find limits. So let's take a look. Let's say we have this. We want the limit of the function 1/2 x squared. So we want to figure out what this is equal to as x approaches, and this should be, as x approaches 1. Yeah, I wanted to make sure because I had to change some slides. So let's take a look at a graph of that then. So we're going to look at graphing the parabola 1/2 x squared. So we know at 0, at 1, or -1. When we square that, we get 1, and then we take half of it. So it's going to be up at 1/2. And here's also going to be up at 1/2. And then if we go out to 2, 2 squared is 4. Half of that is 2. So here we have the parent function, y is equal to x squared, but we are shrinking it vertically. All right, so our parabola is a little wider than normal, so it looks like this. And we are looking at what happens as x approaches 1. And here's where our x is 1. Okay, so if I take a look, if I come in from the left and I look at the y value as I get closer and closer to an x of 1, we see that the y value is getting closer and closer to 1/2. And then if we take a look at the limit as we come into the right on 1, as the x gets closer and closer to 1 coming in from the left, we see that the y value is also reaching 1/2, but it's coming up underneath 1/2. So the limit here is the y value then as the x gets closer and closer to 1 on either side. So our limit is 1/2. So that's kind of a graphical approach. And then a numeric approach is looking at values then. If we're looking for x getting closer to 1, well, we can do a table of values and we can approach the 1 coming in from the left. So like 0.9 is fairly close to 1, but 0.99 is even closer, and 0.999 is even closer yet. So as x is approaching 1 from the left, we see that the x value is getting closer and closer to 1 this way. Let's go down and look at the value of the function then. So if we look underneath, we see then that the y value is going from 0.4 to 0.49 to 0.499. So it is approaching the value of the function, or the y, is approaching 0.5, or 1/2. Okay, now let's go in from the other side. Let's come in from the right side. So from the right side, 0.11 is fairly close to 1, but 0.01 is even closer, and 0.011 is even closer. So as we get closer and closer to an x value of 1 from the right-hand side, so as it gets closer, so as x approaches 1 from the right, we see that the y value then starts out here at 0.6, and then it goes to 0.51, and then 0.501. So it is getting closer and closer to a y value of 1/2. So therefore, the limit of that function, the function 1/2 x squared, as x approaches 1, is 1/2. Okay, so that's a graphical and a numerical approach to looking at limits. So let's take a look at this one then, and let's do the graph of it also. Also, you can go ahead, if you want to pause this, put it in your calculator and see what it looks like. I will take this, though, however, and I will look at the x squared plus 4x plus 3. I recognize that that's a quadratic that is factorable, so it will factor into x plus 3 over x plus 1 all over x plus 1. And then what happens is the x plus 1 is a factor in the numerator, and I have an x plus 1 in the denominator, so those two will reduce out. So actually what you're going to see then when you graph it is a line, and that line has a y-intercept at 3, and it has a slope of positive 1. So if I go back 3, then it's going to be crossing over here. Okay, so here's our line, but the only thing is, because I originally started off with an x plus 1 in the numerator and denominator, I'd know from this original function that I will not be able to evaluate this for -1. So at -1, I'm going to go on the graph. I follow the -1 up here, and right here at -1, there's a hole in the graph. Because if I substitute in a -1 and evaluate the original function, I end up with the 0 in the denominator. Okay, so on your calculator it looks like a line, but if you evaluate that function at -1, you see that your calculator will leave a hole where the y is and say, well, there's no value for y. So you can't graphically see the hole on the calculator, but you can, force it to tell you, well, is it evaluated for that particular number or not? Okay, so, oh, and then I covered up this, and actually, this one I wanted to change. I can't tell if I changed it or not here, but this is the limit as x approaches -1. Okay, so if I take a look at this graphically then, I see that as I come in from the right side and I get closer and closer to -1, so the x is getting closer and closer to -1, so we want to know what that y value is approaching. And the y value is approaching 2. Okay? And then as I come in from the left and I get closer and closer, as the x values get closer and closer to -1 coming in from the left, then that y value is getting closer and closer to 2 also. Okay, so the limit then from a graphical approach, it looks like 2. All right, so let's plug these in, and we have to add then a negative on each of these here because we want to go to a -1. So just add a little negative sign because we want to know what happens as it approaches -1. So we're going to get closer to -1 from the right and the left. Okay, so if you plug this into your calculator, and then you go into the table, and in the table set, you make sure that the x is on the ask function so that you can put in your own specific values here. Okay, well, let's start here. Let's say we want to get closer and closer to -1, and we're going to put in -0.9, -0.99, and -0.999. So we're coming closer and closer from this direction, so from the right, and we want to see what's happening to the y values. So if you evaluate this from your table, on your table function in your calculator, see if you agree with what I have. So at -0.9 it's 2.1, at -0.99 I get 2.01. So see, that's closer to 2 than the last one, and if I put in -0.999 I get 2.001. Okay, so we're coming in from the right side on that. So as x approaches -1, and then from the right we'll put a little subscript or a superscript of a +1. That's what that means. We see that the y values then, or the value of the function, is approaching 2. Okay, and then if we come in from the other direction, from the left here again, so we want to get to -1. So if we start at -0.1 and we evaluate that, I got a 1.9, and I get a little closer. So -1 1/100th, I get a negative, oh, I'm sorry, I don't get a negative, I get a +1.99. And I get a little closer yet, a -1 1,000th, I get 1.999. Oop, make that a 9. Okay, and so we can see then as it approaches, it is approaching a +2. But if you try to evaluate it for 2, I'm sorry, if you try to evaluate it for the -1, your calculator is not going to give you that 2. But we can see from looking at these numbers, however, that they're getting closer and closer to 2. So here the value of the function is also approaching 2. So the only way for it to have a limit then is if it comes in from those two sides and it's the same number. Okay, so there are properties and operations with limits. Here are some of the properties, and these are found in your book. So on these, both B and C are constants. So they're just numbers. Okay. So on this one, it says the limit of, let's put in a constant then. So the limit of 2 as x approaches any number, so maybe even 3, is 2. So if our function is 2, so like y is equal to 2, we know that we have a horizontal line up at 2 units. So as we get closer to any x value, here we're saying 3, so as we get closer and closer to it, the y value then is at 2, because it's a constant function, it doesn't change. Okay, here our function is x, so like f of x is equal to x. So let's take a look at that graph then. So we're looking at this guy. And it says as x approaches some constant. How about as x approaches 1? So I'd go up here and the point on the graph is 1, 1. So as I get closer and closer from the right and also closer and closer from the left, If I'm evaluating it for 1, I'm going to get the limit is equal to 1. If I evaluate it for 2, then the limit's approaching 2, because at 2, the y value is 2. Okay, so you can kind of look at some of those properties and see if you can explain them. So go ahead and take a look at these last two and see if those make sense to you. We also have operations with limits, and these become important. I know this looks like, oh my goodness, that's a lot of technical writing there, but these are important. You need to be able to read this and be able to use these. So if we know this, if the limit of a function as x approaches c is L, and then we have another function over here, g of x, and we're looking at the limit of that function as it approaches the same constant, and that limit is k, then it says the first thing is that the limit, if I would just put a value, multiply that function by a 2 or a 3, so if I multiply it by a constant here, then it's going to equal the constant times the limit. Because I know the limit of the function is L, so if I multiply it by a constant in front, then I'll have a constant times the limit over there. So basically it's saying that the limit of a constant times a function is the constant times the limit of the function. Okay, and that'll make more sense as we do some of those problems. And this next one says, oh, and this should be a G here. I just noticed that. So we're taking our two functions, and if we add or subtract the two functions, and we're finding the limit as x approaches some constant, then our limit, the limit of the sums is the sum or difference of the limit. Okay, so if we're just adding two of them together, we know the limit of this function is L plus the limit of this one is K, then our limit is going to be L plus K. All right. The third one says that the limit of a product of two functions is equal to the product of their limits. 4 is similar to that, only we're using a quotient. So here again, you can kind of look at those and maybe see if you can understand what they're kind of telling you. And as we do these problems, then we'll be applying some of these. So like I said, they'll make more sense in just a little bit. But there's different things that we can do, different methods of figuring out limits, and one of them is just a direct substitution, and that's the best way to go. So you need to look to see, is it possible? If I directly substitute in that constant, will I get a number? And if you do, then you're set. If you don't, then we have to find other ways. But direct substitution is always probably one of the easiest ways to do it, so you want to check that one out first of all. Okay, so this one, we want the limit, and notice we have a polynomial function here. Actually, it's a quadratic, a special type of polynomial. So there's our function. We want to know what's the limit, so what's the y value as the x gets closer and closer to 3. Okay, well, we can graph a polynomial, so you can look at the graph of it. On this particular one, though, we're going to apply one of the properties that we just did. It was number 2. If you go back to the operations with limits, if you go back and look at number 2 again, it says that the limit of the sum or difference of functions is equal to the sum or the difference of the limits. So we can spread this out then and make 3 separate functions out of this. Okay. And then this guy here, the last one, the limit of a constant, we had that one. That was I think it was the first property of limits. So if you go back and take a look at that slide, we know that that is equal to the constant itself. So that is 4. And then this was another one of the properties. As we take a look at this one, the limit of x. So remember, x is just the function with that line that goes through the first and third quadrants. And so whatever x is, the y value is the same thing. So we said it, as it approaches 3 then, the limit is 3. So that's where that comes from. And then here with our quadratic, well, our quadratic, we're looking for as x approaches 3. Well, we are able to substitute in a 3. So 3 squared is 9. And then on the second one, we can also use direct substitution. So when we plug it in then, we just get 3 squared plus 3 minus 4, so our limit is 8. And you're just evaluating that. If you plug in the 3 into your x and evaluate that, you get 8. So that is the limit using direct substitution. Now on this one, we say, well, let's try direct substitution first. And in the numerator, we get 125 minus 125, so we get 0. In the denominator, we get 5 minus 5. So we get a 0 over 0. And because we can't divide by 0, then we see direct substitution does not work. So we need something else. We need another technique. So the dividing out one means that we want to see if we can reduce this rational expression. Well, take a look at that numerator. That should look familiar. So I told you needed to memorize that difference of cubes factoring pattern, and here's an example of how we might use it. So in evaluating this limit, I need to see if I could put this in another form. So the first thing we're going to do is factor this difference of cubes. All right, so it factors into x minus 5 times x squared plus 5x plus 25. And that will now be the new numerator. My denominator is x minus 5. And notice that that will be able to reduce out. So I'll get the same thing then if I just find the limit of x squared plus 5x plus 25 as x approaches 5. So now I won't have a 0 in the denominator because I've eliminated that denominator. So now this is a polynomial function, and polynomial functions we can use direct substitution on. So we substitute in the 5 then for the x's. So 5 squared plus 5 times 5 plus another 25 tells us that the limit of that polynomial as x approaches 5 is 75. Sometimes we can rewrite a function in another form. And this particular one, I don't want to use that one either, because here the x is approaching. I think I took the wrong one, the wrong PowerPoint. I had this one set up, and then as I was working it wasn't working very well, and I didn't do the new one. So we're going to do this. We're going to do the square root of x plus 1 minus 1 all over x. And we still want to do the limit, but we want to do as x approaches 0. Okay, so on direct substitution, we can't divide by the 0, so that's not going to work. Well, so we need to keep that same. We need an equivalent form of that, but we really don't want a 0 in the denominator. So remember, another form then is if I have a radical on the top, we can rationalize the numerator. So that's what we're going to do here. So we're going to take something else that we practiced in the last chapter. So we're going to multiply the numerator and denominator by the square root of x plus 1 plus 1. Numerator and denominator. All right, in the numerator then, we will get x plus 1 and then minus 1. And what happens here? These are going to cancel, so we have x. In the denominator, we have x times the quantity, square root of x plus 1 plus 1. And yes, you would distribute it through, but I noticed that I had an x left in the numerator, so it could reduce out this factor of x down here. So, and I don't want that x there, because remember I want to substitute in a 0 for the x, and that will make that denominator equal to 0 again. And I don't want that, but if I reduce out the x, I get this. And now, in that expression, I can directly substitute in the 0. So 0 for the x, 0 plus 1 is 1. The square root of 1 is 1. 1 plus 1 in the denominator is 2. And then I still have that numerator of 1. So now I can use direct substitution, and I get a limit of 1/2. Okay. One-sided limits, if you would take a look at this and graph this in your calculator, you would see that we have a function that looks like this. So the x's are basically canceling each other out. So on the when I substitute in positive numbers of x, the y values are a 1/2. But if I substitute in negative values of x, in the numerator the x becomes positive and the x stays negative in the denominator, so then we get a negative 1/2. But if I substitute in a 0, it's undefined. So these are open circles here. Okay, so all right, so I just resumed again after a 10-minute pause, and I have no idea where I was at. So when we look at this then, as we come in from the right, and I don't know how easy it is to see here, but we have as x approaches 0, see that little superscript of a plus sign? So as we're coming in from the right then, our limit is a positive 1/2. And as I come in from the left, so I come in this way, our limit, see that little x approaches 0 with the superscript of a negative there? So as it comes in from the left, it is a negative 1/2. So I can't evaluate the limit for 0 because coming in from different directions of 0, I get two different numbers. So I could do just one-sided limits. I could calculate, you know, either from the left or the right, but if I try and do it for just as x approaches 0, because they don't match up, we would have to say the limit does not exist. Okay, so D and E does not exist. So those two limits have to be the same thing. Now another thing that might happen when you look at a graph is that you're going to get, it keeps continuing on up forever, and I don't want to do this one either because this one has opposite. I wanted one that would look the same. So let's try this one. Let's go the limit as x approaches 0 of 5 over x squared. Okay. So we're going to take a look at that graph. So I know that the denominator, I don't want a 0 down there, so I'm going to have an asymptote at 0. The horizontal asymptote, this is going to be hard to remember back to when we were doing rational functions in college algebra, but if the degree of the numerator is less than the degree of the denominator, then we also have one at 0. So I have a horizontal asymptote at 0. And because I'm squaring the x, whether I put in a positive or a negative number, I'm getting a positive number then. So our curve is going to look like this. Now I don't have a scale put on there. So I'll just leave it like that, but basically it looks something like that. So as we look at 0, what happens then? As I come in from the right of 0, so as x approaches 0 from the right, I see that it gets higher and higher, so it is approaching positive infinity. And then as x approaches 0 from the left, it is also approaching positive infinity. So they are, in fact, approaching the same thing. So you could say that the limit is infinity, but infinity is basically the same thing as it does not exist, because it's not a number. I can't peg it down. So does not exist. Okay, so basically these two things are going to mean the same thing. All right, and if we had a curve maybe that looked like this, so it's approaching negative infinity from the left and positive infinity from the right, here again, it does not exist. Okay, so that's unbounded behavior. All right, and I think that's pretty good. Here again, just credit to our textbook. And I'm sure you're going to have lots of questions, and you know what? We'll even come up with more questions as we do examples in our book. But that's all right. We will together figure out how to do limits. All right, see you in class.